Thank you very much. So I will resume from the point where I stopped yesterday. So we are considering M, which is a compact, orientable, reducible, heteroidal, three-manifold, and we are going to consider the hyperbolic structure on the interior of this manifold. So at the moment we don't know if such a structure exists or not. So I'm going to show you the two important theorems for such a manifold. So the first one is it's quite general theorem. So I will state it in a general form first. So it's a theorem due to Peter Scott. So it's published in 1970 something, 73 or something for. So the statement is as follows. So suppose, well, I use this n here. So suppose n be a non-compact. Well, if it's okay if n is compact, but then the statement is quite trivial. So that I like to say that, emphasize that the main point is that when n is non-compact, so it's a non-compact three-manifold, and assume that pi 1 of this manifold is finitely generated. This assumption is quite essential. So we assume that. Then there exists a compact three-manifold C embedded in N, so embedded in N, such that the inclusion is a homotopy equivalence. So if we are, so the point is this. So if we assume on this one, so that if we assume the pi 1 is finitely generated, then you can, homotopically, you can realize this manifold as a compact three-manifold. Well, this is quite amazing. So because if manifold is compact, then its fundamental group should be finitely presented. Not only finitely generated, but finitely presented. But here the assumption is being finitely generated, not finitely presented. So this means if the group is a fundamental group of three manifold, then the finite generation implies finite presentation. So this holds only in dimension 3. Or of course, in dimension 2 it holds, but if the dimension is higher than 3, I mean, for instance, in dimension 4, this is false. So you can construct a four-manifold with finitely generated but not finitely presented fundamental group. So this is a special property of three-manifolds. So do you have any question on this here? It's okay? The clear? Yep.
What's the intuitive reason for, like, how do you construct such manifolds?
So starting from n, so you just pick up the generator system and realize it by the loops. So it's a kind of bouquet. So, and then what's important is to, after that, you need a kind of the technique of surgery or something like that to make it homotopy equivalence. And it's very subtle argument. And actually, the Peter Scott published this paper in, as I said, in the 1970s something. And it's a very short paper, and it's quite readable. So I suggest, if you are interested in it, I suggest you reading that. But the same theorem appears in a textbook written by Hempel. It's a three manifold, which is published in a Princeton red series. What's the name? Annals of Mathematics Studies or something. But its proof is wrong. So you must read the Scott original paper to understand this. So don't read the Hempel's book for this one. Okay. Now this is one of the main results concerning that. So it's as the corollary. If we have a finitely generated torsion-free Kleinian group and consider the corresponding hyperbolic free manifold, then it contains compact reducible heteroidal three manifold, orientable C. Reducibility is a homotopy invariance. It has a homotopy invariance. This one is reducible. Because the universal cover is H3, that should be reducible. C should be reducible. That's a consequence of the Scott theorem. And this property, this also comes from that. So that if you have a torus in the hyperbolic three manifold, I should say that as a fact. If a hyperbolic three manifold contains an incompressible torus, then it must correspond to a torus cusp, something called a torus cusp. So it must correspond to torus cusp. That means you can homotope it into something called torus cusp. So what's torus cusp? So in PSA2C, you can classify the elements into three types. So one is for an element in PSA2C, one type is elliptic, meaning that it's a kind of the rotation around some axis in H3. And the second type is parabolic, meaning it's conjugate to this type of matrix. The third type is called loxodromic, or some says it's a hyperbolic, it's something conjugate to a diagonal matrix where its absolute value is greater than 1. So this should be also the conjugate to that one where the absolute value is equal to 1. Okay, it's just a classification of a matrix. It's if you consider the Jordan standard form of the matrix, then it turns out that there are only 3 possibilities for an element of the PSL2 theory. Okay. And so if a Kleinian group contain, well, if a Kleinian group contain a subgroup, where isomorphic to a rank 2 abelian group, then this should be so well for G, then we can conjugate G so that this rank 2 abelian is just something like so it's a parabolic subgroups. Okay. It's easy to, well, it's not so easy, but it's not so difficult to show this. Just if you have a abelian, then abelian subgroup there, then well, you can show that the two, and if you pick up 2 generators, then you can show that first you can show that they should both you can diagonalize or well maybe you can conjugate them to a Jordan standard form by the same matrix, and so that means the both of them so after the conjugation, the generator should have both of the generators should have this form or that form. We are now assuming that it's torsion free, so that we don't. Well, actually, even you have torsion that property holds, but we are not going to consider that case. So we are considering parabolic and so by the way, so if you have Kleinian group contains an elliptic element, then that must be torsion. So in our assumption we are not considering the elliptic elements. So they should both have that form or that form. And if you have abelian groups, rank 2 abelian groups, whose generator have both of whose generators have this form, then you can show that it cannot be discrete. So that means the only possibility is having this form, and that means both of them should have that form after the conjugation. Okay. So geometrically, this means so in an N. Oh, it's not the N. It's H3 over G. Okay. In H3 over G, you have something called cusp. So it's a quotient of, so in an upper half space model, it's a quotient of the part. So where it's a point where the imaginary part is greater than some constant, and if you mod it out by this group, then you get something like torus times half-hop interval, and that's what we call the torus cusp. Okay. So any incompressible torus in a hyperbolic 3 manifold, sorry, this should be better, must be homotopic into such a cusp part. So that's the consequence of this. Okay. Is it okay? Any questions?
Could you go over again why the torus comes out from the inequality?
Comes from here?
The torus cusp part, why the cusp has a torus, shape of torus.
Okay. So, well, I'm using some facts. So that if you have such a group, you can find K, sufficiently large K, such that any element of G either stabilize it or move it to something disjoint from that. So, and the stabilizer of this part is exactly this. So this group. So in a manifold, if you take the quotient of this part by this group, you have something embedded there. So that's what we call the torus cusp. So if you mod it out by this action, then on the boundary you have a torus. So at any level you have a torus. So you have a product of a torus with a half open interval. So that's what you have here.
Comment is that because the metric gets smaller and smaller as you go up, so the torus should get the level as smaller and smaller. That's why it looks like not the torus crossing to the torus.
Yeah. This is a topological picture. So in a geometric picture, because of the hyperbolic metric, as you go upward, the torus, the area of the torus tends to 0. So it's like so a real picture should be like this, and this is torus. Okay. And that's the reason why it's called cusp. So this implies so when we are considering the MM, and then because this part is a cusp, and then so in an M is a compact 3 manifold, so to compactify it, you have to attach something like torus times infinity. So it means any torus. Any incompressible torus should be homotopic into a boundary component. That was the definition of this being a toroidal. So C must be a toroidal. Okay, or maybe because C is. I'm sorry. So that should be like this. So that C should have some boundary component like that. So, or obtained by cutting the cusp neighborhood. So, and if any torus is homotopic into that, then it has to be homotopic to this component. So that implies that C is a toroidal. Okay. So I haven't compactified it yet. So that I'm sorry. So I'm considering the submanifold now. So the C should be something obtained by cutting this part. And so that was Scott theorem, or sometimes it's referred to as Scott's core theorem. Such a C is called a compact core, or Scott core. Okay. Now, the second big theorem, well, is due to Bonahon, Ego, and Kalikari. Goodbye. So it's a kind of something called tameness. Suppose G is a torsion-free, finitely generated Kleinian group, and consider the quotient of the hyperbolic 3 space by this group. Then by Scott core theorem, you have a core. So this is a compact core. Then so they show that actually interior of C is homeomorphic to H3 over G by a homeomorphism homotopic to the inclusion. So, as I told you yesterday, even in the case when the manifold or the group is isomorphic to the fundamental group of the closed surface, if you consider the hyperbolic 3 manifold corresponding to the quotient of such a Kleinian group, it's not clear at all that the quotient is homeomorphic to the product of the closed surface and the open interval. So this is a generalization. And I said the Bonahon proved that it's actually homeomorphic to the product of surface and the open interval. And this is a generalization of Bonahon's result for a general 3 manifold group. Actually, Bonahon first proved this for something called freely indecomposable groups. In Ego and Kalikari, they showed independently that even if you drop that condition, the tameness holds. So again, this is very difficult theorem. So to understand that, probably you should first read Bonahon's paper written in French, and then understand their argument, which generalized Bonahon's.
So it's equivalent to say that each component or complement of C is the product.
Oh, the equivalent of saying that you can choose C so that the complement is a product. So in general, the freedom of choice of the C, and okay. And this paper was published, but the Ego's paper was not published. So it's but you can find it in the archive as a preprint. So this shows that. So this will imply that space of the hyperbolic structure and the space of the faithful discrete representation of the pi 1 can be identified as in the surface case. So, and then next theorem is, but still we don't know, well, we haven't showed yet for such M there exists a hyperbolic structure. So the existence of a hyperbolic structure is another problem, and it's very difficult to show, but it was proved much earlier than this by Thurston. So M is as before, so it's compact orientable, reducible, and toroidal. Then interior of M admits hyperbolic, complete hyperbolic metric. So in particular, he showed that something called geometrically finite hyperbolic metric exists in the interior of M. And plus something called the minimally parabolic, meaning maybe the without rank 1 cusp. I will explain what the meaning of the rank 1 cusp later. So at the moment you can ignore these two adjectives, and then just look at this sentence. So the interior M admits some complete hyperbolic metric. Actually, for Thurston, we should assume the boundary is not. So yeah. So we are considering the case where boundary is not empty. So in a closed case, it's true, but we need some assumption if we just rely on Thurston's work. So after that, the Perlman showed that in general it's true, but at the moment what we are interested in is the case when M has a boundary, because otherwise there's no meaning for the deformation space, and we would like to consider deformation space, so we assume boundary is not empty. Okay. So any questions for this one? And the proof of this one is probably the hardest among all the theorems I stated or I'm going to state. So to prove that, well, you need something like if you prove it in quite in details, then you need more than 500 pages to prove that. Okay, so Thurston himself stated it in 1978, I guess, right? And he intended to publish the proof in a series of papers divided into 7 parts. So the first part was published in Annals of Mathematics. And for the second part and the third part, preprints exist, and you can download it from the archive. Yes, but from the fourth part to 7th part, nothing exists. So if you want to understand first and original proof, what you can do is just guess his proof, reading the part which exists. But
then how do we know that he proved it?
oh, so he gave a lecture, a series of lectures on that topic, and the lecture notes exist. And if you read it carefully, very carefully, I mean, if you read between lines, then you can understand he really proved it. And actually, the detailed proof exists as a book. So Misha Kapovich, for instance, published a book from the Berkhäuser and containing the kind of complete proof of the first one, this theorem. Or some, there's a survey paper by John Morgan, which is the oldest, and also Jean-Pierre Otard wrote some survey paper, and they both contain the essential part of the proof. So you can, if you can read it and just interpolate the something lacking, then you can understand. So Kapovich's book is the most complete one. So it contains almost everything. But his approach is different from the first and original approach. So he uses technique invented after the Thurston's paper. For to know Thurston's original approach, the best one is John Morgan's survey. So it's quite faithful to Thurston's approach. Okay, so I'm not going to talk about that. So we assume these three theorems. Then now we can talk about three kinds of the definition of the deformation space. So the first one was, as before, it's H of M. That is the set of hyperbolic matrix on interior of M and modulo some equivalence relation. So the equivalence relation was the same as before. Two matrices are said to be equivalent if there is a diffeomorphism homotopic to the identity, or not homotopic, isotopic to the identity, such that the one is obtained from the other by pulling back using that diffeomorphism. Okay. So that's the first definition, and the second definition is was as before. It's a faithful discrete representations of pi 1 of S, pi 1 of M into PSL to C modulo conjugacy. And for the third one, I need to define something corresponding to a Fuchsian representation, and for that I need something more. So I first consider these two definitions. So as before, if you have a hyperbolic metric on the interior, then you can consider holonomy. So you can consider the universal cover and identify the universal cover with the hyperbolic free space, and then pi 1 of M acts as isometries, which are the covering translations. So you get the representation of pi 1 of M to PSL to C. Okay. So that means HM is contained contained in a AH of M. Okay, so this is just considering holonomy. Okay. So in the case of surface times interval, this was equal. But in general, the equality doesn't hold. So AHM is a union of disjoint union of H N. Well, I'd like to let something F here, probably. F here. So where H and F is a space, it's just H of N. Where N is some compact, reducible, compact orientable, reducible, heteroidal, three-manifold, such that F is homotopy equivalence from M to N. So you just list up the compact three-manifold homotopy equivalent to M, and take the such a space H and consider its union. Then you get AH of N. So I should remind you that in the case of surface closed interval, any compact irreducible three-manifold homotopy equivalent to the surface closed open interval is surface closed open interval itself. But in general, the homotopy equivalence doesn't imply homeomorphism. So that's why we have to take some union there. Yep.
In general, how many the pair of N and F?
Yeah, I'm going to talk about that. So, but by the way, so this is so two homotopy equivalents. So regarded as the same if the these are equivalent if this one. Well, in general, you don't have the inverse of that one because this is not a homeomorphism, but you can consider homotopy inverse. So there's a map from N1 to M, which is homotopically inverse of the F1. Then this is a map from N1 to N2, is homotopic to a homeomorphism. Then these two are regarded as the same. So this union is taken over this set of the equivalence classes. So now I'm going to answer your question. So actually we understand very well what the homotopy equivalence is between the two compact three-manifolds. So homotopy equivalence is between two compact reducible heteroidal manifolds. So I should divide the argument into two sub-cases. The first case is when, so we are considering some compact reduced by toroidal manifold M. So first case is when M, boundary of M is incompressible. So let me recall you that, well, here the incompressibility means the injectivity of the pi 1. So here, what we are assuming here is a boundary of M. So if you consider the fundamental group of a component of boundary of M, then it's injectively embedded into pi 1 of M. So that's the assumption. So in that case, there is actually two kinds of homotopy equivalence which generate the general homotopy equivalence. The first is something like that. So if suppose M has some submanifold, three-dimensional submanifold, well, maybe something like that. So suppose M contains a three-dimensional submanifold of the form sigma cross interval, such that such that sigma times 0 and sigma times 1 lie on the boundary. And the boundary of this one non-contractible, so it is not null homotopic, non-contractible on boundary of M. So the picture is like that. So you have some surface with boundary and times I, and if you consider this surface times 0 and times 1, they both lie on the boundary of M. Then you can flip. So you can cut this part out, and for one component, well, what matters here is the case when sigma has more than one component actually. So you cut it out, and we glue it back. But when you glue it back, you just change the direction of the I coordinate of one component. So maybe if I write the two-dimensional analog, it's easy to understand. So you have something times I, okay, and you glue it back in this way. So you just flip the one of the I direction, okay. So in a two-dimensional case, this also gives a homotopy equivalence, but what you get here is a normal orientable surface. So in this way, you can get normal orientable surface homotopy equivalent to the original one.
So is this to add some sort of twisting?
Twisting, yeah, it's a twisting, but in the case of the two-dimensional manifold. In this case, it's just because twisting means nothing in a three dimension, so it's just a flipping of the I coordinate. So that's the first kind of homotopy equivalence. And the second kind of homotopy equivalence is, well, maybe I should go there.
Are we assuming the boundary of this product region is the boundary component of the Riemann, or
Well, so the no sigma must have boundary. So the boundary of sigma is not empty, and well, if it has only one boundary component, then what you get is just a trivial homotopy equivalence. So we assume this has more than one boundary component, and more than one component. Okay, so the second case is something like this. So you have a solid torus embedded in three manifold. So V and V. So in this way, the intersection of its boundary and the boundary of M is union of non-contractible annuli on boundary of V. So that means you have a solid torus, and for instance, you have a something like this. You may just draw the parallel copies of this. So here you have three, but the possibility it's more than three. So you have, for instance, something like this. And homotopy equivalence can be defined if you have such a solid torus by this way. So you cut it out and glue it back by after changing the order of these annuli. So cut V out and glue it back after changing the order of these annuli. Or these annuli, or maybe it's better to its complement is better to understand. So the order of the gluing part. So changing the order of this might be confusing. So maybe it's better to regard it as changing the order of this complement part. So it's the order of the annulus, which lies interior. So it's about the complement of the intersection is probably in interior of this one. So you change the order of these annuli. So cut it out, maybe change this part. So you glue it back by changing the pasting part, this to there and this to there. Then you get something which is homotopy equivalent to the other. Because so in the eye of homotopy, you can just shrink this annulus to just a circle. If these three parts are glued into a circle, the order means nothing, because they meet each other in a long circle. So in a homotopical, in the sense of homotopy, the ordering means nothing. So you can change the order, keeping the homotopy type the same. Okay? Any question up to here? So actually, in the case when the boundary is incompressible, so essentially these two are the only possibility of the homotopy equivalence. So any homotopy equivalence can be generated by these two kinds of action. So that's what Jake O'Shara and Johansson proved. So any homotopy equivalence, well, M was a irreducible, compact irreducible toroidal, and in the boundary M was assumed to be incompressible, is obtained by iterating the flipping, maybe maybe several times, maybe iterating, well, maybe iterating flipping, and this one. So this should be called the shuffling. So iterating flipping and shuffling. Okay. So that's the answer. So if you just consider any combination of flipping and shuffling, then you get some homotopy equivalence, and they are all. So these two operations generate all homotopy equivalence from the M to some complex free manifold. Okay. Okay, so is it okay? So that's the case when the boundary is incompressible. If the boundary is compressible, then there is another kind of homotopy equivalence. So a typical example of compressing boundary is something like this. So you suppose you have, for instance, genus 2 surface, and consider the product of the genus 2 surface and the interval, closed interval. And you attach one handle here, like this. So its handle is just this closed interval, and you attach it so that the disk cross 0 and disk cross 1 lies on the top boundary here. Then what you get is a compact irreducible heteroidal free manifold with two boundary components. One boundary component is here, it's a genus 2 surface, and the other boundary component is here, which is a genus 3 surface. Okay. So this has a compressible boundary because so here you have a disk. So on the boundary this is a non-contractible curve, but in a three manifold this bounds a disk. This bounds a disk. So meaning that in the fundamental group of three manifold it's trivial, but on the boundary it's non-trivial. So the pi 1 doesn't inject. So it's compressible case. So in this case, the homotopy equivalence can be constructed in this way. So just remove the handle, and instead of attaching them to the top one, just consider this kind of attaching. So one component is attached. Component is still attached on the top, but the other component is attached to the bottom. Okay. So these two are not homeomorphic. It's evident. So here you have two boundary components. The top one and the bottom one. Here, the boundary is connected. So because the number of boundary components are different, they cannot be homeomorphic to each other. So these are not homeomorphic, but these are homotopy equivalent. Why? Because in the idle homotopy, you can just shrink this part to just a surface. So make it a surface, and this handle can be shrink into this arc. So this and something these are the same. Just attaching an arc to a surface. So they are homotopically the same. They are homotopy equivalent. Okay. So, yeah.
So this compressible condition is similar to that in closed condition in dimension 2 case. The closed surface condition in dimension 2 case. There was a theorem that the closed surface with homotopy equivalent must be homotopic to homeomorphism.
Yeah. But here you have a homotopy equivalence which is not a homeomorphism. So these two are not homeomorphic, but homotopy equivalent.
So that corresponds to non-closed surface case.
Non-closed surface case. Non-closed surface case, yes, in a sense, because the number, you can change the number of the boundary components. Yeah. Okay, so actually, this is a special case, but in general, if you have a compressible boundary, then you can regard it as an incompressible boundary, union of incompressible boundary and a handle. And if you have a handle, you can just consider such a kind of operation. So for any three manifold with compressible boundary, you can consider such a homotopy equivalence. If it has more than one, actually, if it has more than one boundary component. But anyway, so you can consider such a kind of thing.
Can I ask a question?
Yep.
Given that the boundary is compressible, does such decompositional wave always exist?
Exists. So you have such a part.
Okay.
So it's something called characteristic compression body. So such a manifold is called compression body. So a special case of compression body is a handle body. So it's something like that. So any three-manifold with irreducible three-manifold with compressible boundary has something called characteristic compression body. That should be compressible. That should be compression body like that, or handle body. So in the case of a handle body, you don't have such a kind of operation, but except for that case, you can consider such operation. So the Jacob-Sheridan-Johansson theorem can be generalized to the compressible boundary case. So that's a theorem by probably McCullough and Miller. So they say that this operation, so the Jacob-Sheridan, so the shuffling, or flipping, shuffling, and this operation generate homotopy equivalences, or homotopy equivalences. So again, in this case, you can show that there is a kind of enumeration of all homotopy equivalences. So we know that what kind of the union you are taking. I overrun the time. So maybe I should stop here. And we take a break, and after that, I'm going to talk about quasi-conformal deformations for this general setting.